Hey, hear me out. Pi is one of the most extraordinary numbers in mathematics. If we had the ability to fundamentally change what number pi was, mathematics just falls apart. You can't change it. It would be like changing the amount of sides on a triangle. It just doesn't work. It is also one of the most famous, 3.14. Who doesn't know that? But that number continues on and on endlessly. Even if we can't see all of them, by going to piday.org, they have the first 1 million digits of pi listed on their website. Scrolling through it shows you just how many there are. I'm scrolling as fast as I possibly can. But by going all the way to the bottom, we can find that the 1 millionth character of pi is 1. No matter how much more pi you discover, there will always be more. It's unending. It's infinite. But what does it mean to be infinite? What even is infinity? How big is it? And what lies beyond infinity? Can you count past infinity? Well, let's slow down for a second. First, let's try to get there. We're going to have to come up with some really large numbers really quickly. To help us, maybe you propose a Google, which is 10 to the power of 100. Or maybe you thought of the vastly superior Googleplex, which is 10 to the power of a Google. Or maybe you thought of a millinillion, which is 10 to the power of 3003, which is a 1 followed by 3003 zeros. Perhaps you thought of just standard scientific notation, which is any number times 10 to the power of any number. But might I propose tetration, an exponent tower like this, x to the power of x to the power of x to the power of x. Let's plug 1 in for all of these x's and see what it gives us. Well, shoot, that only gives us 1. So let's go on to number 2. 2 to the power of 2 to the power of 2 to the power of 2. Any guesses what this equals? Nope, because you're lazy. 65,536 is the answer. A pretty large number, granted we only use the number 2, so let's step it up to number 3 to show how hard this scales. The answer? 10 to the power of 3.6 trillion. For reference, there are 10 to the power of 80 atoms in the observable universe. It is unfathomably large, but let's say that this number here is applesauce's number. So let's represent it with an @ sign and plug it back into the tetration we just did. Applesauce to the power of applesauce to the power of applesauce to the power of applesauce. Surely now we're almost at infinity, right? Nope. You are no closer than when you originally started. Now we approach a decent understanding of just how large and unobtainable infinity is. Our human minds can only comprehend so much though, and just like you'll never truly understand why I'm suddenly dressed like a frog, you'll never truly understand the size of an infinite set. But to illustrate it even further, applesauce's number, if you will, is gargantuan. If I had an applesauce amount of peach pies, it would span a distance of not 1, not 2, not 3 universes, but a millinillion universes, times 10 to the power of 3.6 trillion. You can't even comprehend that, and yet you are no closer to infinity than where you started. So, how do you describe something that is endless? Well, it's complicated. Because we can't particularly prove infinity exists, I mean, how could you? We have to make an axiom. An axiom is basically a rule that we assume is true. We can change it or delete it later, but for now, it's all we've got. The axiom of infinity states that there must exist an infinite set. Such a set can be represented by Aleph Null. Aleph Null is about the best that we have when it comes to our particular infinity. It describes the cardinality of that infinite set. A cardinal number basically describes the amount of something. So if I were to take these pies, their cardinality is 12, 4 long and 3 tall. 12 is the cardinality. I can put numbers 1 through 12 with each of these pies. So the cardinality of infinity is Aleph Null. So there, we did it. We've achieved infinity. We have counted it. Not so fast. We've only counted that particular infinity. There are more. How do we achieve those? Is it possible? The answer is a resounding yes. What we found in Aleph Null was describing a countable infinity. We can count every step along the journey, even if we will never reach infinity. For instance, try this. Let's count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Pretty simple. But if you were to count every possible number between 0 and 1, things get a little bit more tricky. Well, we got 0 and 0.00000000000, and therein lies the crux. At some point to define step 2, I have to put a 1. Otherwise, 0.00 forever is still just 0. So I need to put a 1 to define we're going somewhere. But at any point in that journey where I could put a 1, I could put a 0 instead. And then if I put a 1, that number would be smaller. But then I can just put another 0. It is impossible to define step 2 of counting all the numbers between 0 and 1, making it an uncountable infinity. So, surely we've done it. We have discovered the largest infinity. It is quite literally uncountable. Its cardinality is the continuum. But that wouldn't be very true. There are still larger infinities yet. We just have to reach them. To do so, let's go back to an old friend. The first countable infinity, Aleph Null. But we have to count past it. And to do so, we run into some complications. Let me show you. The problem with counting past infinity is that infinity plus 1 will always equal infinity. To illustrate this, welcome to Hilbert's Hotel. In Hilbert's Hotel, there are an endless amount of hotel rooms, going on infinitely, but each room is filled with a guest. So how do we make room for this new guest in the hotel? Well, let's start by moving him to room 1. But we only want one person per room, so let's move the guy who was in room 1 to room 2 to room 3, and so on and so forth. And we continue this all the way down the line. Even though we get to the end of my illustration here, we know that this guy has a room to go to because the rooms are endless. There will always be another, so we put him over there. Now, despite accommodating for an extra guest, the result is no different from when we started. You can do this endlessly. Let's move each guest to double the room number of the one they are currently in. So 1 to 2, 2 to 4, 3 to 6, 4 to 8, and 5 to 10. And you keep doing this for each room. And the result is startling. Even though each room was full without changing the amount of people, now all of our old guests occupy even number rooms and odd number rooms are all vacant. We can add an infinite amount of people now to these odd number rooms, and again, we are no different from when we first started. We just added infinity to infinity, and nothing changed. Now, I can understand why that would be confusing. By taking an infinite amount of people in a full hotel and moving them to rooms that are only even, we're basically saying that even numbers are equal to all numbers. But how does that make sense? I mean, half of all numbers are even. Well, count with me again. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Goes on for infinity. We know this. But you've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And that also goes on for infinity. No matter what number you have, in this illustration at least, if you multiply the number that you have by 2, you will always have an even number to match it. You can do the same thing with odd numbers too, although it's a little harder to demonstrate that quickly. But at the end of the day, all even numbers or all odd numbers are equal to all numbers. No matter how much we try to add, multiply, or exponentiate, we will always still be within the confines of infinity. So, how do we get past it? And what do we do if we've used every number in existence that is countable? What would be the number after that? In order to surpass infinity, we need to stop relying on cardinal numbers. Instead, let's utilize ordinal numbers. Ordinal numbers don't tell us the size of a set, but they do tell us in what order they should occur. And this is extremely important, and I'll show you why. Imagine you're going to a concert, as well as an infinite amount of people. Each person has been given a ticket with a unique number on it. Because there are an infinite amount of tickets, by definition, we have used every single countable number in existence. But here's the catch. Everyone else gets into the concert, but then you appear. So, what number gets put on your ticket? They're more than willing to let you in, but what number do they use? Well, this is where we have to use the first infinite ordinal, omega. Your ticket would be given the number omega, which isn't bigger than infinity, but it comes after it. Now that you've gone into the concert, the group of people, even when you are added, is still infinite. Its cardinality is aleph null, but we added someone to it after we used all countable numbers. And you can keep doing this. If more and more people come, you can keep adding 1, 2, or 3 to omega by doing this, omega plus 1. Now, don't do 1 plus omega. Order very much matters here, but we can now let that person in, and then omega plus 2, and let that person in. But we know we can count to infinity using the axiom of infinity. We can pretend infinity is completable, and then we can go 1 past that. So, omega plus omega. Isn't that just omega times 2? So we can multiply. Well, we know from 2 we can count to infinity and beyond, and suddenly we have omega times omega, omega squared. We're flying now. Well, let's do tetration again, exponent towers. So we got omega to the power of omega, to the power of omega, to the power of omega. Now, normal math notation would stop there, but you can keep going. It would just be unfathomable. Remember, the tetration tower of 3 that I showed you was insanely large when you calculated it out. This is on another level, but we can keep going endlessly. But that is epsilon's not. So we can condense that, and then you can keep going. Now, I didn't feel like researching how to keep doing this because, to be honest, you're chasing your own tail. You can have epsilon naught to the power of epsilon naught to the power of epsilon naught infinitely, and you get epsilon 1. But, again, you'll never reach the next step. But if you were able to count every single countable ordinal, you would finally reach omega 1, the first uncountable ordinal. Believe it or not, we are well on our way to probably never losing another game of I Love You More. Lord forbid, I Hate You More as well. Omega 1 is so Brobdingnagian that it will never be quantifiable by any means. Have fun looking up that word as well. But the idea is simple. Even though it's unquantifiable, we can still keep going. Omega 1? Well, why not omega 2? Using the axiom of replacement, we can go all the way to omega. But I would caution you in using this number in a game of I Love You More. Because when we want to describe how much we love someone, the words how much means cardinality. We want to say how much we love someone, we need a cardinal. If we were to use an ordinal, it'd be like, well, I love you in the order of. Well, shoot. Love isn't about an order, it's about magnitude. So let's find a cardinal for omega. And lucky for us, there is one. Aleph omega. And we know that Aleph omega is bigger than Aleph null or Aleph 1 because it has to be. it by definition is bigger than those that came before it. So, hi Mom. Hi Dad. Hi to all of my loved ones. All of my friends. I love you. I love you to Aleph indexed by an infinite tower of omegas. And while there are larger numbers out there, I didn't even go into inaccessible cardinals. Good luck finding them, and at the very least, you can't just throw +1 at that one. From the bottom of my heart, thanks for watching. Peace!